All right, so yeah, what I'm doing is probably turned completely on its head compared to most everyone else does. Most everyone else is going to present here with machine learning. Rather than looking at data and doing machine learning on data, I'm doing machine learning on models. So it's a little bit weird. So as I said, as was pointed out with the introduction, let's see, the laser is there. Yeah. So there's this stuff, dark energy, that's according to the standard lore, most of our universe, but we really don't know what it is. So let's figure out what we can say about it, or what we might be able to learn. So begin with just going to go over what makes a good question. After that, if we have time, since I know not everyone in the audience is necessarily versed in cosmology, I'll spend a little bit of time talking about standard lore and data sets so that you have some context for this. And then discuss work in progress and talk about the model that I've been working on for this. All right, so getting into it. So when I talk about a question, what's a good question is far too general. But what's a good question to ask to find evidence for something other than the standard model is a little bit better. Can maybe start working towards that. And I'm also taking a Bayesian perspective here, where when I say ask a question, what I really mean is how do I construct a model and use data to update priors. So if you're going to try and avoid wasting your time, you want to try and ask questions that have the best chance of updating your priors, changing your mind. And since for something like dark energy, we really don't know what's going on. We have lots and lots of models. Any particular theorist can walk up and talk to you about the model that their prior favors. But we would like to have really general, we'd like to have the ability to ask really general questions here. Which, of course, doesn't work so well. Something that people who work with data science will be more familiar with is curse dimensionality. You are always limited in the number of dimensions you can work with. Because if you have too many parameters, it becomes difficult to constrain your model, and you run the risk of overfitting. So what we want to do is, since we simultaneously want to ask really general questions, but we can only do it with a few parameters, what we need to do is figure out how to target which parameters we use. So, okay, so to find something that can update your parameters, you have to be able to claim that if you find something, update your prior, you have to claim if you find something, it can't be explained by your standard model. For example, the standard model for dark energy is just a cosmological constant. I don't care how beautiful your theory is, if it doesn't predict something that looks substantially different from a cosmological constant, no one's probably going to care all that much. So, put another way, what we need to do here is to find, in terms of data analysis, we need to find modes that have signal from our alternate or extended model, but not too much noise, and they shouldn't be something that gets excited by degrees of freedom in the standard model. So just treat them both like contaminants and treat this as a filtering process, which we can phrase as a generalized eigenvalue problem. So here, sigma E is the prior covariance matrix in the space of predictions for your alternative model. N is the noise covariance matrix that you get from the experiments or data sets that you're working with. And sigma lambda is like sigma E, but just for the standard model. Here it's lambda because I'm looking at dark energy, so my standard model is just a cosmological constant. So here, kappa is a control parameter. If kappa gets very large, when you solve this generalized eigenvalue problem, any modes that are not orthogonal to the span of your sigma lambda get suppressed. And so they'll have a small signal to contaminant ratio. So in general, we're going to be working with large kappa limit. It can't take it to infinity for numerical reasons, but you still want it to be large. So if we can solve this problem, then we at least know where we can look to maybe be able to find answers. All right, so this part has already been done. So it was a paper where we were looking for not to see what models could be found there, but just is there a chance that there is possibly signal in the cosmic microwave background that could have come from a non-standard primordial power spectrum. So what we did was we made an extended model where we took lambda CDM and then we added Fourier modes. We just added sinusoid perturbations on top of the power spectrum. And we got modes that look like this. Again, I'm talking about CMB, so these are multiple moments. So you get modes that don't look like what you see, but also aren't just completely noisy, because they do reflect some aspects of your extended model here. And so this particular mode matches with that point on this graph. So if you look at this, we did not find a statistically significant detection of anything here. I mean, this is pretty boring. But one thing I did want to point out about this mode is we're pretty sure we know where this almost 3 sigma detection you would get if you did the wrong thing, ignored everything else, came from. And it has absolutely nothing to do with the primordial power spectrum. We think it's beam leakage that the Planck collaboration figured out after the fact between the TT and TE power spectra. So just knowing where in the data you might find signals from something novel doesn't mean you know what model you would find if you look there. So you have to instead find some way of relating the the degrees of freedom to model parameters. And then you can vary those parameters, and you are actually testing the model. So the generic idea you want to do is to find a submodel, or if you think about it as a manifold, you want to find a lower dimensional approximation to that manifold, which is something that probably sounds more familiar to machine learning people. There is a classic technique that's been used for this sort of thing in linear algebra. You just use the modes themselves as coordinates. And so you basically pick an origin and then add coefficients, and then you walk along the different directions as dictated by your coefficients. And you can generate a lower dimensional model this way, which is, again, just a standard technique. It's just principal component analysis, PCA. You can rephrase our signal to contaminant problem as PCA just by performing a whitening transformation here. And then you have exactly just the standard PCA. However, there's sometimes a problem. So let's suppose that we have some elliptical prior. So this would be like a Gaussian prior, and I'm showing like maybe a 2 sigma bound here. And let's say that we don't know this ahead of time, that this direction is actually responsible for most of the variation in the predictions that we would find. So once we model this prior in the space of predictions or potential observations, once we've done this whitening map as well, you don't necessarily always have something, it's not always a linear model, so you don't always end up with an ellipse again. So if you then try and do PCA, you can still do it, and it'll tell you that most of the variation is happening in this direction. Okay? Well, if you then regress from that onto the parameter space, you'll find kind of a weird curved thing, because you're not really following the distribution you have. And so this tends to lead to poor quality low-dimensional approximations. You might walk away from the best case for the best lower dimensional manifold you can find, and you might walk off from valid parameter ranges because you're not really, for example, out here, sure, there's variation out to that far, but if you start at your origin here, your ellipse didn't go there, so you're distorting your prior if you do this. What we would like to have happen instead is to find something that can do this. And then we regress and we can get a better lower dimensional approximation. There is such a technique by Matthias Schultz. It's called hierarchical nonlinear PCA. So once you can phrase the problem as PCA, which we do with the whitening transform, it's just a matter of training a neural net to find your principal curves at this point. So what's going on here is that you deal with curve distributions by learning a nonlinear map. So you have, it's an autoencoder. So you have a minimum 3 layers. So you do a nonlinear map. Then you have the linear autoencoder sandwiched in the middle to do your PCA. And then you map back so you can straighten out curved distributions. The hierarchical part comes from the way the training's done. So your error function is a sum of the error function you would have if you only considered one component, the best component, or if you only kept the first 2, plus what you get if you only kept the first 3, and so on and so forth, or however many you want to keep. So by doing this, you actually get out the actual eigenvalues from that eigenvalue problem. Just a generalized version. So, comment on regression. You want to stay within the bounds of your prior because it's not infrequent in physical models to have forbidden regions of your parameter space that don't make any sense. And if you're not careful about how you do regression, you'll just walk right into them and not notice. So, keep it simple. Nearest neighbors is a really old machine learning technique, if it even deserves to be called that anymore. It works as long as you have a convex prior. It's going to work. And in my experience, it works more reliably than fancier methods that I've tried. So, an example of this, it's well known that if you look at the temperature spectrum only for the CMB, you can only constrain 5 of the 6 lambda CDM parameters. So if I wanted to ask what submodel, what submanifold would reproduce this, reproduce the variance that lambda CDM itself would predict if you're going to just measure the temperature, I can do this. And I can ask which mode is the worst, which one should we cut out? And this method exactly hands back to me the degeneracy that is known between the optical depth and the amplitude. The degeneracy just comes from if you have a higher optical depth, you lose more photons before they get to you, and so you have a strong degeneracy between the overall amplitude, A, and the optical depth, tau. So this is the mode that gets cut out. So it's just a quick check for people who are used to think in terms of cosmology that yes, this does actually find the submanifold that you want. So, summary of learning what questions to ask. You just want to, what I mean by questions is you're posing them parametrically. So you're coming up with some model. If it's too general, I mean if you can answer everything you want with just a few parameters, then you have no need for this. But if your question is too general, you can use this signal to contaminant analysis to target what parts might be answerable. There might be some parts with all the data sets you have on hand that you're not going to be able to answer. And there's nothing you can do about that. So you shouldn't waste your computing time modeling that. And then use this combined NLPCA, or if you're really sure you've got linear mapping, PCA is fine. And the whitening space to, don't know what the feedback was, to get parameter curves. All right, so really quick dark energy overview, because I don't want to run over too much, and I don't know how long I've been going. So standard law, have a hot, dense universe. It's expanding. The expansion kind of slows once we get to the matter-dominated region. But if you look out here, we're finding accelerated expansion. So it's not just coming out constantly. It's actually curving outward. That's representation of the acceleration. So that means that there has to be something driving it. The standard law for that is that there is something called dark energy. Probes I'm going to use, I don't want to take time to go into these in depth, but you can use supernovae as standard candles, and combining redshift information and the luminosity, you can constrain the expansion history that way. You can do the same thing with baryon acoustic oscillations, which imprint a characteristic separation between masses in the universe, so galaxies, galaxy clusters. You can also use strong lensing time delays. So if you have a strong lens and light gets focused to you by two different paths, you're going to have different path lengths. And so when you get something like this, you know that transients that appear show up at different times. So you can actually measure the time delay. And using angular separation and redshift information, you can predict what that time delay should be. Again, letting you constrain the background evolution. Then, of course, there's the big one, the CMB, which is, this picture is a snapshot of the universe early on. It's just the photons have taken so long to get there, we're just now seeing it. Get to us, we're just now seeing it. So, this includes temperature, polarization, which tells us a little bit about the scattering that's happened, and lensing, which tells us about what the light has passed through on the way to us. Combined, the temperature and polarization break that degeneracy I mentioned and can completely constrain, or reasonably well constrain, the lambda CDM parameters just by themselves, not using other data sets. And if you have other perturbations, they'll be sensitive to it. Whereas the lensing power spectrum tells you something about the development. And possible effects, that if you have dark energy perturbations or something like that, messing with the standard expectation for how things develop. So, quickly going over the theoretical description of how we model dark energy. The standard way to model the background evolution is just in terms of the equation of state, in terms of this parameter W. Accelerated expansion necessitate W is less than minus 1/3. Use the same description for other more familiar things, say photons, it's 1/3, non-relativistic matter, it's 0. So there's this constraint if you're trying to build a model that W cannot cross -1, or else all the perturbations will diverge and your universe will blow up. So that obviously isn't realistic because our universe looks pretty nice. And just because if it's less than -1, it's called a phantom, this gets called the phantom divide. So current best fit, if you suppose a constant W is really close to -1, and if you have lambda CDM, if you have a cosmological constant, that's equivalent to W being fixed at -1, so it's not crossing it, and there are no perturbations for this, so it's okay. So going beyond just the background, we might want to look at the microscopic physics of the theory. So what's actually going on in this fluid that we're modeling? So you can look at, say, the speed of sound in the fluid, and potentially you can look at weak coupling. So if you have too strong of a coupling, it's going to change the background evolution. And so also if you test for perturbations, which are not the 0th order anymore, you might be able to rule out models that otherwise you couldn't. So now just briefly to talk about the way I'm approaching dark energy with this, and again, this is work in progress, so unfortunately I don't have results to show you today. I hope to, but it didn't work out. So in order to make a model capable of investigating and get around the phantom divide, I propose a 3-component dark energy model. This is just a phenomenological model. I'm not saying that nature actually does this. I'm just saying we can model what we might be able to see with something like this. So And if you want to look at each non-standard component, we can make this function out of a positivity-preserving spline, such that if you give it a bunch of positive knots, any point along the spine is positive. And of course you have to invert that for the less than -1, but it's the same idea. And if you draw values for the knots from a prior, like a beta distribution or something like that, you can make sure that you can do this, and you can generate very general-looking curves. And so I am, with what I've been doing, letting the speed of sound float as a free parameter. And at this point, I have not yet put in couplings to other fields or between the dark energy components. So, in summary, if you use the signal-to-contaminant analysis with hierarchical nonlinear PCA, you can find lower dimensional manifolds that approximate your full distribution, which perhaps have more to do with your actual parameters than if you just shove a linear manifold in there. By incorporating a number of different cosmological probes, you have a better chance to be able to see evidence for something other than cosmological constant, and hopefully there'll actually be something up on the archive relatively soon for a result for this. Thank you.
Okay, thank you very much. Are there any questions?
Thank you. I just had a question about a combination of PCA with nonlinear PCA that you mentioned. And I was wondering, what is the benefit of using this combination into datasets? Is it just about the time complexity, or there are some datasets that actually using the combination of these two algorithms has better results than using one of them?
Perhaps I miscommunicated something, but other than perhaps as pre-training for the neural net, I don't use them at the same time. It's an alternative. You can do this without any machine learning. You can solve it exactly if you're really convinced that you have a linear model. But in general, that doesn't always work out unless you pick a very small parameter region where you can only keep the first term in a Taylor expansion or something. So don't use them together except as pre-training to help get the nonlinear PCA neural network going.
So you said that at first we should divide the data set into separate sections, and in each different sections we should use PCA or nonlinear PCA.
So I'm proposing them as alternatives to NLPCA as the right way to do this sort of thing, as opposed to the PCA way. So it's just going from parameter, is this the picture you were talking about?
Yes.
Yeah. So on one side we have the parameter space, on the other we have the predictions that are associated with those parameters. So I'm not dividing up the data set, I'm just mapping between the two spaces. Does that clarify? Okay, thank you.